Yeah, let's start then. Okay, so my screen and video, everything is clear, right? And my voice, everything is clear, right? Video. Okay. Good evening. I mean, my voice is clear, right? And video and the screen, everything is clear. Please confirm someone. If there is any problem, then I have to do something. Yeah, I hope everything is clear. So let's start then. Good evening, everyone. My name is Milan Kumar Mal. Uh, Not audible. Not audible. Now also, right? I'm not able to.
Sir, voice is not coming.
Oh, okay, 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 okay. Just a minute. I have to then leave the call. Yeah. So, yeah. So I will do problems analogous to those problems, so that it may help you to solve those problems. Actually, we are not supposed to do exact those problems. So we'll do analogous problems so that you can solve those problems. And also we will discuss here any type of problems regarding the course content, or if you are facing any type of problem on this subject, this linear algebra, so you can ask here, or you can directly mail me. That is ma21d0. I will write the mail here. So you can mail there, or you can ask here also in classes. So we will try to solve those questions. And when you are watching a lecture video, and if you are facing some problem, I mean not able to understand something, then before posting the problem as the link of the video, if you try to one thing, that just take the screenshot of that particular portion where you are not able to understand, and post that video, post that to the post that in the I mean, wherever you are asking, either in discussion forum or in someone, that's okay. So okay, so today is advanced linear algebra. First tutorial 1. Okay, today is 25th January. Okay, So, um, okay, first of all, we have done solution of linear equation either in class 10 or 9. That is, suppose we have a system of equation. We have done the 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 solution. How to find? No, we know how to find solution of a solution of two equation in how to find solution of two equation in two variable. Suppose you have a x and y are variable, x1 to y equals to, suppose this is b1 and or y1, no, not y1, b1, and you have a21x plus a22y is equals to b2, and you know how to solve this problem. You can compare x finding from both equation and compare them and to get the solution of for y, and after that you can after that you can do after that you can replace the value of y in one equation, so that you will get the solution of the other variable. So this is the way. Suppose you have three variable equation. Instead of this, if you have this equation ax y a1 2y plus a13z is equals to b1, and a21x plus a22y plus a23z is equals to b2, a31x plus a32y plus a33z is equals to b3. Similarly, you can do same thing, to proceed the same way to get the solution of the system. Now thing is that suppose you have a larger number of variable, so then there will be larger number of equation as well. So in that case, doing this process like comparison or multiplying one equation by some constant and adding with other, in that way, if we try to do, then in that way it will be little tough, because there will be lots of things will be there. So that's why we need a general setting, a general idea. So how to solve those type of problems. So from there we came to the system of linear equation, and that system of linear equation will be given uh, by a matrix that I will discuss. So let's take a system of equation. Let a system of linear equation, a system of linear equation is given by like a11 x1. Let's take x1 x2 xn is the variable, so then it will go all the way a1n x1 xn, which is equals to, let's take b1 or y1 is not variable here. Okay, a21 x1 plus all the way it will go a2n xn is equals to y2. Let's in this way, we have m equation, a m1 x1. This is just coefficient type of things. This is just coefficient type of thing, that is nothing to do with mn xn is equals to yn. So here we have total m equation is there, m equation is there, and total m equation is there, and n variable. Note that n variable is there. Okay, what are the n variable? These variable are x1 x2 xn. These are the variable. So now question is that suppose we don't know, I mean n is a large number, so in that case we can't do the previous process like multiplying one equation by some constant and multiplying the second equation by other constant and adding them, I mean as per the requirement of that constant, adding them to cancel to reduce one variable. So we can't do those process here, because I mean we can do those process, but those thing will be little problematic, because there is a lots I mean number of variable can be large. So in that case, what one can do? One can do the, I mean, introduce the notion of elementary row operation. So before that, one can write this system of linear equation in this way. One can write this system of linear equation by ax is equals to y, where y can be written as a column vector y1, y2, yn, n by 1 column vector, and a can be written as the matrix a11 all the way it will go a1n, and am1 all the way it will go amn. Okay, this way one can write, and x is the variable column, that means x1, x2, xn. Now if we consider this is as a n m by n matrix, this is as a n by 1 matrix, and if you do the usual matrix multiplication, you will get that you will get this thing you will get. Okay, so system of linear equation can be given, that can be written in this form. Then a is called the coefficient matrix. A is called coefficient matrix. Now what are the some tasks to do? Our task will be like, when the system will have solution, if there is this solution, then what are the number of solution? I mean, it can be either zero, it can be either a number of solution is either zero, number of solution can, if it is possible to be finite, or if it is possible to be infinite, all those things. Okay, but before going to that portion, I'm just trying to recall quickly whatever is there, and then I will do problem. So before going to that, so what we need to know, that whatever the operation we are doing here, that multiplying one equation by a constant and adding it, and again multiplying other equation, and I mean multiplying one equation by a constant, and multiplying a second equation by constant and adding that. So before doing those things, I will try to do the similar things where in this system of linear equation a1 and x1 plus a1 and x1. Okay, so those operations are called elementary operations. What are the elementary operations? Elementary operations, there are total three elementary operations. Those are those are like, first, one can multiply a scalar to the equation. One can multiply, I mean, just exact term, it would be better to use the exact term, that is, one can multiply, multiplication one row by a scalar. What is scalar here? Scalar means the entries, these entries ay, a1, an, these entries can be aij, can be the element of real number r, aij can be element of a space complex number, aij can be coming from anything. Aij can be, if anyone know the finite field, then aij can be coming from a finite field also. Aij can, I mean, here, as you are in a system of real or complex number, so either it will be coming from real, or it will be in general coming from complex number. So scalar is that element. A element of the field is called scalar. Okay, I mean, from where these entries are coming actually. Don't If you don't know field, all these things, then don't be nervous, because all these elements are coming from either real number. You can assume those are coming either from real number or from complex number. That is will be enough. So elementary operations, multiplication of one row by a non-zero scalar. Okay, because why it is non-zero scalar? Because if you take zero, then that equation will be vanished. That's all. I mean, you can't multiply equation zero. That equation will be vanished. So that will not be effective actually. Second thing is that you can add one row by another with another row. Replacement replacement of a row, or here is the of rth row of A by row R plus, or you can multiply here also, plus C times row is. Main point is that suppose you have two row. Here is one row and here is one row. You can multiply one row by a non-zero scalar and add that, or I mean you can multiply this row, you can multiply a scalar and add here. Okay, you can do that thing. This is the what it is means. Okay. Second is interchange of two row. Third is interchange of two row. Okay. Okay, so you can interchange two row. So these are the three elementary operations. So recall that multiplication by one row by a non-zero. For example, we have initially this one. We have that initial example a11 a12 8 y is equals to, suppose we have b1 a21 x plus a22 y is equals to b2. What we in general do, we will multiply a21 here, we will multiply a11 here, and subtract it, right? So or in other word, we can multiply minus a21 here and add those things. So after multiplication it will be a11 a21 x plus a12 a12 minus a21 y is equals to b1, that will also be minus b1 a21, and here it will be a21 a11 x plus a22 a11 y, which is equals to b2 a11. Now if we add these two these two equation, what you will get? You will get this one is 0, this sum will be 0, that means 0 dot x, and other will be like a22 a11 minus a12 a21, those into y is equals to, similarly will be something. But now consider this is a system of linear. This is a matrix form: a11, a12, a21, a22. Now this is equivalent. Whatever we are doing here, this is equivalent to here. What is that? That is just multiplying this row by a non-zero scalar. First step we can do multiplying this row by a non-zero scalar a21. First step is this. We'll multiply non-zero scalar a21, and after that, so what it will be? It will be minus a21 a11 a12 a21. Okay, a21 a22, it will be. Now what we'll do, we'll just add this. Now what we'll do, that row 1 plus a11 row 2, we will do this operation. First with row 1 we'll add a11 row 2. Then what will have, that first will be 0 first term, clearly, because row 1 is this term and a11 with row 2 is this. And I will have what is that? That will be a11 a22 minus a12 a21, and similarly, and whatever it is, a22. So we will get a new equation. That equation is this one, right? So this is the what is the mean by elementary row operations. Okay, we will do these operations are give a form and name as elementary row operation. And so these are the actually elementary row operation means, and what elementary row operations actually do. They are not doing anything special, they are just adding, or adding to equation or multiplying a non-zero scalar to a equation. That is what elementary row operation is doing. Interchange of two row means interchange of two equations. Suppose we have three equation, here we have three equation. If we interchange second and third position, both side, you will write this one in below and we will write this one in above. That will not change anything. So this is the interchange means okay. So but they are affecting on the, they are doing something on the matrix level. So that's why these three operations are fixed. Okay. Now now what it means, now if you know that, suppose you have a system of linear equation this, and you know a solution of this system, right? So now after row operation you will get another system of linear equation, and that system of linear equation and solution of this system, suppose uh, so let's take this is just one. Let one be a system of linear equation. Okay, A be a system of linear equation, and b11 x1, we have mentioned b on the right hand side, so b will not be here. So let's take, this is something different. C11 we can take, C11 x1 all the way it will go, suppose C1n xn, which is equals to some b1 prime, and it will go Cm1 x1 all the way, it is go Cmn xn is equals to bn prime. So now this is bm prime, this is m equation, bm prime. So now this is the system, this is the new system that is coming by elementary row operation of the system 1. So but if there is a solution of system 1, then that solution will also be a solution of the system, this system 2. Okay, so so that means if let, that means what it means, let ax is equals to b be a system of linear equation, system of linear equation, and a dash x is equals to b dash is obtained after elementary row operation, obtained after a finite number of elementary row operation, finite number of elementary row operations uh, on ax is equals to b. Then solutions means the x1 x2 set of x1 x2. Solutions means this x1 x2 xn, those values of x1 x2 xn for which we will have this equation. This is a equation, this is a set of equation, it's written in a matrix form. Okay, solution means this. Then then solutions of ax is equals to b will also be solution of ax, a dash x equals to b dash. Okay, similarly if ax equals to b is obtained from a dash x equals to b dash, then by elementary row operation, then solution of a dash x equals to b dash will also be solution of ax equals to b. Similarly, if ax is equals to b is obtained from ax is equals to b by a finite number of elementary row operation, finite number of elementary row operation, then solutions of row operation from on finite number of elementary row operation on a dash x is equals to b dash, then solution of a dash is equals to b dash will also be solution of will also be solution of ax is equals to b. What I am saying, suppose we have a system of linear equation ax is equals to b. Okay, now after elementary row operation we are getting a new system a dash x equals to b dash. Okay, then solution, I mean those variable set of x, set of variable x1 x2 xn for which this will satisfy, that means the system of linear equation, that means a finite number of equation will satisfy. So those x will also be solution of this, that means for those x also these equations will be satisfied. And suppose a dash x is equals to b dash, from this we get ax equals to b after finite number of elementary row operation, then this solution of this system will also be solution of ax is equals to b. So that's why if, for example, if b is equals to 0, then if b is equals to 0, that means, what is mean by b is equals to 0? B is equals to 0 means this is 0, this side is 0, here it is written y. If this is 0, then whatever elementary row operation, that means addition, scalar multiplication, whatever we do, the right hand side term of the equality will always be 0. I mean, suppose I have two equations where the right hand side is 0. So in that case, whatever elementary row operation we do, right hand side still be 0. So if y1, y2, yn are 0, then whatever elementary row operation we do on that system, in this system, this b1, b2, bm dash, this will also be 0. Okay, or y, I think this is the intention to write y1 dash to ym dash, because that will be, this will also be 0. So a system for which a system of linear equation ax is equals to b, for which b is actually 0. 0 means 0 column. 0 column. Then ax is equals to 0 is called a homogeneous system. So for example, if ax is equals to 0 be a homogeneous system, and after elementary operation you are getting a dash x is equals to 0. So in that case, whatever x satisfy this side, ax equals to 0, that will also satisfy a dash x equals to 0. Similarly, if a dash x equals to 0 gives the, but after elementary row operation x equals to 0, then whatever x will satisfy this, those x will satisfy this. So that's why, and we know a and a dash are said to be elementary row equivalent, are said to be if and only if one of them can be obtained, one of them, if and only one can be obtained from other by a finite number of elementary operation. Each one can be obtained from the other if and only each one can be obtained from other by a finite number of elementary row operation. Okay, finite number of elementary row operation. So that's whatever we said here, that if ax equals to 0 is a system, that is homogeneous system, and we have a solution. So those solution will work as a solution of a dash equals to 0 whenever a dash x equals to 0 is coming by a finite number of elementary row operation on ax equals to 0. Similarly, if a dash x equals to 0 has a solution, I mean has a system of solution, and ax equals to 0 is obtaining from a dash equals to a dash x equals to 0 by finite number of elementary row operation, so then both of them have same solution. So that is the reason when A and B are row equivalent, when row equivalent, if one can be obtained from, each one can be obtained from the other by finite number of elementary row operation. That means if we have A, by finite number of elementary row operation you will get A dash, and from also, as it is saying that for each one of them, that means A dash also can be obtained from A by a finite number of elementary row operation from A. So that's why both a and a dash, both ax equals to 0 and a dash equals to 0 will have same system of solution. That is the reason. That is the reason. So this is the reason actually. That is the reason. So we can write. So if a and a dash are row equivalent, so if a and a dash are row equivalent, then ax is equals to 0 and a dash x dash equals to 0 will have same number of solution, will have same set of solution. Why it will be set of solution? Okay, that I am just coming to you. So I mean, so same set of solution. Moreover, one thing you can note that will come as you know that I'll just pointing out that set of solution of a homogeneous system Ax equals to 0 Ax is equals to 0 will form a vector space. As I have not said about vector space, so that I will not say, but that is clear to you hopefully. That we will discuss when we will recall vector spaces. Okay. So that is the reason someone is asking in discussion forum, when a two matrices are row equivalent, so why in that case we will have the same set of solutions. So that is the reason. So if there is any doubt, whatever I am speaking or saying, you can ask me directly right now. That is not a problem. So now, so this is the reason. So and I just want to point one more thing. What is happening when elementary operation is what is let I mean one way I have seen that when elementary row operation is happening, I mean when we do elementary row operation on a matrix, that means we are just adding or scalar multiplying and then adding those linear I mean linear equations. Okay, but that is in as a system of linear equation. But I just want to point out on the matrix level. I mean, for a system of linear equation, there is two things. A system of linear equation you can say as a collection of linear equations that way, or you can say it is a form of ax equals to y. That form you can say. But what I want to point out here is that when we do elementary row operation on a matrix A, then what is happening with that matrix actually? Okay, that is what I just want to say. Let let A be an elementary A be an n by n matrix, m by n matrix. Okay, on a either real number or complex, that doesn't matter. So, and if I mean that matters only from where I mean when the elementary row operation is doing. So in that case, the choice of the coefficients are coming from either on that field, either from real number or from complex number. So let A be an M cross N matrix, and A dashed is obtained from A by a finite number of elements. Obtained from A by a finite number of elementary row operation. Elementary row operation. Okay, so what is happening when we do a row operation? So multiplication, I just want to, this is what is happening when we do elementary row operation. One thing we have seen is that when we are in matrix, when we are in linear equation system, so in that case, elementary row operation is just, I have said it three, four times, that elementary row operation is just multiplication by a equation by a non-zero scalar, adding a linear equation with another and interchanging to linear equations. But here what we will discuss is that what is happening on matrix level. So for that, suppose you take a n by n matrix A. This is the n by n matrix. Let's take this. This is the m by n matrix. A1n, A m1 to A mn. This is an m by n matrix. Now I do an elementary row operation. There is three elementary row operation. Let's take the first one. What is first one? That is multiplication by a non-zero scalar. So that means multiplying this matrix from the left hand side, that will be m by m matrix, left hand side, that is 1. Suppose I want to multiply it is on the rth row. This is the rth row, Rn, this is the rth row. Okay, so I want to multiply this rth row by a non-zero scalar C. So what will happen? This matrix will be A1 on, all will be as it is, all will be as it is. Just let's see that non-zero scalar which I want to multiply. Then this will be CARN, and all will be all will be as it is, right? This is supposed to be done, but from how I will do C into row R. I am multiplying C to row R. But that is equivalent to saying, I mean, that is equivalent to multiplying this m by n matrix by this elementary matrix. This will be at rth place C, and all other entry will be 0, and it will be like here 1, and all the way it will be, that is 1. So this is the earth place of main diagonal. Okay, so this is the matrix. This is the matrix. This is the matrix. Matrix with all diagonal entries. Matrix with all diagonal entries are 1 except 1 except earth 1 earth position, which is C, and all other entry are 0 are equals to 0. This is the thing. I'm not able to write here properly, but okay. So this is this matrix is multiplying. My point is that this earth row operation, that means multiplying the earth row by a non-zero scalar C, is just nothing but multiplication by this is an m by m matrix. How this is happening? Let's see. This one will multiply this, and I will have this a11. Whenever this will multiply the second row, this will be second row first element, like this it will go, and you can check this. Okay, so this is what happening. But the second thing is that interchanging of two row, that is interesting. What is happening? Suppose I just want to change r and s position. Okay, interchanging of two row.
Sir,
Yes, yes,
sir, whatever elementary operation you are doing, it
yes.
is only for whether the solution is existing or not. That one only we are seeing or any other purpose.
Elementary row operation is, I mean, matrix is mainly coming whatever in linear algebra is, that is for whether that is, I mean, that is coming in, initially it is coming as a um, what else, as a system of linear equation, but after that matrix can be used. Okay, elementary row operation are doing for only to for the solution of a system of linear equation, you can say that. Okay, you will not be used it for any other thing. Yes, you may use it for to get the inverse, but that is also the saying same thing. Why it is saying same thing? Suppose you have a system of linear equation this. You just want what is x here, right? So if you know what is A, and A is a square matrix, and if you know what is A inverse, then you can multiply A inverse on both sides and get x equals to A inverse B. Then this will give the solution. Okay, so that is, I mean, inverse, finding inverse for a square matrix only, because if you are not getting taking square matrix, then you will not get the inverse actually. So, so that is the reason, that is only this is the purpose. I mean, main purpose is to get the solution.
Okay, thank you.
Yeah. So now let's say we do the second elementary operation, interchanging of two row, interchanging of two rows. So how suppose I have the matrix A11, and I will do interchange A1n, A1n xn. Sorry, there will not be x. I'm just writing in matrix level. I'll write it in little bigger font. This is the thing. Um, A1n, and suppose um I am taking R row and S row. AR1, ARN. This is the R row, and after some point it will have S row, S1. What is my point to saying what elementary row operation actually doing as a multiplication of a matrix? There is a purpose that I'm just trying to say. ASN, and all the way I will end at AM1 to AMN. Okay, this is the matrix, for example. Now what we will do? We will do in not interchange. Let's take first take. This is the uh, let's take R plus some scalar of RS. This is the operation I am doing. Multiplication, adding R row with multiplying S through C and adding with R through. That is the what we will say. So what is actually this operation actually will reflect, that I am just trying to say. So in that case, we will do like one Just a minute. Yeah, what we'll do, multiplying, just a minute, multiplying second. Yeah, so we'll write at R position is 1, yeah, and it will be 1 0 0 0. It is as it is, and it will be like that way. R and S, multiplying. If suppose, for example, suppose I have 1 0 2 1. If we multiply this is with two equation, what is happening? This will be a1 1 a1 2 a2 a1 1 plus a2 1 2 a1 2 a plus a2 2. So if we multiply s by c, so at s position we'll write c, and where you will replace it, yeah, that is the thing. For example, I'm writing, so in that case what will happen, it will be as it is only at rth row, only at rth row, because I will replace it by earth. This will be replaced at earth place. Okay, so that means this will be a11 all the way a1n and ar1 plus c as1, comma all the way arn plus c asn, and it will be as s row will be as it is ASN, AM1, all AMN. So S row will be as it is. So Rth row is, this is the thing. So we will have Rth row. In Rth row, what I will write in Rth position, uh, 0 all the way. It is, there will be an Rth position. This is the RR position. There will be multiplying first equation. Yes, R position, it will be 1 at the diagonal, that is earth position, and after that at s position, it will be after that at s position it will be c. I'm multiplying c 0 0. All element, all other element will be like as it is as diagonal. Okay, so this matrix will be something, this position I'll just mark. This position is actually, this is R comma S position. So there will be only C. This is what. Okay. So but whatever C is that, first note that this matrix is invertible, right? Just I am replaced the Rth position on the diagonal C, and every element is C, 1. That is diagonal. Here is also diagonal is 1. There is no affecting with diagonal. What we are doing is that only writing one more extra element at the RS position, that is C. So that means this matrix is also diagonal. Now we'll do the third operation. What third operation says is that interchange of two row. Interchange of two row. Suppose I want to change R and S position interchange. So there, what will happen? Suppose we have the matrix. This is the thing: A1, 1, 1, A1, N, and AR1. This is the rth row. And after some time, we will have, suppose, S row, ASN, and all the way AM1, AMN. Okay, I want to interchange this R and S. That is interchanging row R and row s. This is what we will do. So that means this will go here and this rth row will be here. Okay, so for that purpose, what we will do, we will interchange R and S column, that is of identity matrix. that is 1 0 0, and we just interchange R and S position, that is also denoted by RS. So um, suppose R is initially, so what will happen, R will be below and S will be here. So this will be like this way. um, the matrix I'll just writing it is as a no, it will write as a matrix also, not a problem. 1 0 0 0, this is the thing. And suppose, just let me check, 1 1 a12 a21 a22, I just want to interchange first and 2, so that's why my claim is that I will interchange 0 1 1 0. So if you multiply a21, if you multiply a22, this will be a11 a12. So interchanging rth row and s row, so rth column and s column, that is what. Yeah, R column and S column. So suppose R column is here, so that will be there, and S column is here, so this will be here. So this is the thing. This will be this is the diagonal. This will be 1, and this will be 1, and all other entry are 0. Like all other entry will be as it is. Like here it will be 0 0 0 all the way, and this. Okay, and suppose this two row. This is actually, this will be rth row. This will be sth row, and 0 1 0 0 it will go. After that it will go 0, and it will go after that also 0, and it will go 0 0 0 0. It will be at the point, at the end it will be 1. I mean, this is what I'm just trying to say is that I'll just writing the point positions. This is RR position, RR position. This is RS position. This is a S R position. Yeah, and this is SS position. We just interchanged, I mean, just interchange two column, something like that. Okay, so in that case also this matrix will be invertible. My main point is that in this case also matrix will be invertible. So that, but what we are saying, elementary row operation means, suppose we have a matrix a suppose we have a matrix a11 a11 a1n and a m12 a mn, and we are doing elementary row operation. That means finite number of elementary row operation. That means what we are doing, we are just multiplying this left hand side by elementary matrix like a e11, those things. Okay, this type of matrices are there. So this is what so this elementary operation means, this is what we are doing actually. So but after whatever, if we do finite number of operations, so each of them, each of this matrix, this matrix, this matrix, and all of these are invertible. So that means after elementary row operation, we just, if we multiply all of this elementary row operation, we will get a matrix P11. So P1n, all the way this is M, this is 1M, M1 all the way PMM. So this will be M by N matrix. So we are just, what we are doing, we are just multiplying by a invertible matrix. That invertible matrix depends on the, what are the elementary row operation we are doing on this system of linear equation. So what my point is that if we have a matrix A, and if we are multiplying by a invertible matrix P, that means we are doing some elementary row operation on A. So that is what we just, my point is that, so therefore let A be an M by N matrix, then a finite number of elementary row operation is just nothing but multiplication, multiplying A by a invertible matrix, multiplying A by a invertible M by M matrix, depending on the elementary row operation. I mean that elementary, I'll just add those elementary row operations. Suppose we have initially the matrix A, we have done a elementary row operation, so that means we are multiplying this matrix. After that we are doing another elementary row operation, that means we are multiplying again the resultant matrix, multiplying by a new n by n matrix. So in that way, ultimately whatever, if we go finite number of way, this is equivalent to saying that just multiplying this matrix to this particular main matrix A n by m. So this is what means this matrix, this matrix will be called, this matrix are combining to form the elementary matrix P. Okay, so this is what happening. So this depending on the elementary row operation. This is what I just want to write here. Depending on elementary row operation, elementary row operation, and conversely, if a dash is if a dash, or I can write PA is equals to B for some m by m invertible matrix P, then B is just a finite number of elementary row person, finite number of B just obtaining from A, B just obtained from A after a finite number of elementary row operation, number of elementary row operation. So this is what. So why we are saying this? Because there is problem which I'll do. Okay. For example, this is the problem. This is the matrix. This matrix I will do. Okay. So this is the first matrix, and I will do sum of the problem on the basis of whatever we have discussed till now. Okay. So on that basis, we will do sum of the problem. Okay. So let's take this matrix. Let A1401. Let A is equals to 1401. If I'm not 010, a 4 by 5 matrix, 010, and second matrix is 210 minus 10, second row, 210 minus 10, 210 minus 10, 18020. Okay, so 18020 into 01201, 01201. So what is mean by this? 21401014010, 210 minus 10, 210 minus 10, 18020, 01201. So now suppose we have, this is the matrix. Okay, so what are the, I mean, there is a lots of questions one can obtain from this matrix, one can do from this matrix. So first is that suppose we have this matrix, then one can ask what are the solution, which I have not discussed. I will discuss later. What is the, I mean, what we can do after elementary row operation on A. Okay, so this is our problem that I will do. So here what is that? So it is asked that to do that row 2 minus, here it is, the question is that let A equals to this matrix. Okay, so I will do this here. This will be better. Suppose I have the matrix this, and P denote the elementary matrix which replaces row 2 by this row 2 minus 2 times row 1, and row 3 by row 3 minus row 1. That is one. So first, suppose row 2, this is the row 2. So from there we will multiply row 1 by 2. Let's multiply row 1 by 2. What it will be? It will be 28020. And second is that second is as it is, and we will subtract this from row 2. So first will be as it is, 010. This is the thing after elementary, first elementary row. This is the row operation we are doing here. So if we subtract from this row, this particular row, what we will have? we will have first 0. After that we will have 1 minus 8, that is minus 7, 0 minus 0 0, and after that minus 1 minus 2 minus 3 0, and all will be till now, all will be as it is 0 and 0 1 2 0 1. This is the thing. Now if we do, after this, if we do this operation, that row 3 minus row 1, so this is the row 3. If we subtract it from the row 1, what we will have? Row 1 will be as it is, 0 minus 7 0 minus 3 0 1. Acha, I am just subtracting, it is from row 3, so this will be 0, this will be for row 3 minus row 1, 0 2 minus 1 1 and 0, and what it will be as it is. So what is happening here is that, so what is the answer is that, okay, sorry, question was different. Okay, sorry. Let P denotes the, then what is the elementary matrix? Okay, sorry. Let P denotes the elementary matrix which replaces row 2 by row 2 minus 2 times row 1 and row 3 by row 3 minus row 1. So that means, so in that problem, so what it will be, just row 2, we are asking for P, which which is doing this thing, that PA will be a new matrix A dash, in which will obtain from A by two operation. One is row 2 minus 2 times row 1. I'll write it symbolically. Row 2 minus 2 times row 1, and that is be replaced by row 2 dash. And second is that row 3 dash is equals to row 3 minus row 1. So if we do, we are doing two things. One can do that, we can do these two operation with A and get A dash, and one can multiply a suitable matrix P on A and to get A dash. So question is then, what is the A dash here then? Okay, so sorry, what is the P here then? So what we will do, we can do this. Let's take the elementary row operation. uh, so we have know that for these two particular elementary row operation, what is the matrix actually, right? So for that particular elementary row operation, here it is 4 by 5 matrix. So matrix P will be P, two matrix is there. One is the elementary row operation, first one, which is corresponds to this one, we will write. And what is that? That will be, this is corresponds to the replacement of row 2 dash is equals to row 2 minus 2 row 1. Just check once, I'm correcting. Row 2 by row 2 minus 2 row 1. Row 2 by 2 row 1. So for that, I will write 1 0 0 0 this. And row 2. So 0 2 here it will be minus 2. Because if you recall here, what we have done, if we are multiplying C with row S and adding with row N, then on the row of R, I mean R row, we are adding it, we are replacing R row by, we are replacing R row by R row, we are writing, actually you can write here, R row equals to R row plus C into RS, row S. So that's why what we have done, identity matrix there, we will just one extra term, C, where it is on the rth row, S column. This is what. So here we are doing same thing, right? We are doing replacing R2 by R2 minus 2R1. So here S is equals to 1 and R is equals to 2. So in the row 2, that means this is the row 2, I will replace the first S column, that means first column, this minus 2. Here C is equals to minus 2. And identity matrix will be as it is. And no change will be done. This is what first elementary matrix. Now corresponding to the second operation, that is R3 dash is equals to R3 minus R1, right? Replace row 3 by row 3 minus R1. So that means this will correspond the elementary matrix, corresponding elementary matrix, corresponding elementary matrix. And here what will be corresponding elementary matrix? Similarly, we will replace row 3. So we will go to row 3 and all will be as it is. At diagonal. Row 3, but S is here 1 and R is here 3 and C is here minus 1. This is what. And in particular case, I will just write all these things. what is happening in this particular case, that S is equals to minus S is equals to 1, S is equals to 1, R is equals to 2, and C is equals to minus 2. So this is also doing here. So what we will get? We will get minus 1, 0, 1, 0, 0, 0, 0, 1. We will just go in which row we are replacing, we will go that row, and whatever row we are multiplying and adding it, we will replace that column. Okay. So now if we multiply E1 first and after that E2, this is the thing we are doing actually with the matrix A, right? So then after that we are getting matrix A dashed, which is obtained by these two elementary row operation. So that's why P will be actually, this is the matrix. So let's take P is equals to E2 E1, right? So P will be E2 E1. What is E2 here? 1 0 0 0 0 1 0 0 minus 1 0 1 0. This is the E2, and E1 is 1 0 0 0 minus 2 1 0 0 0 0 1 0 0 0 0 1. This is the thing. So first will be 1, second will be 0 0 0. This with this 1, this with this. This will be minus 2 here, this with this, this with this column will be minus 2 here, and after that it will be 1 0 0, and this column with this with this will have minus 1 here, right? Yeah, minus 1 here, nothing else. Minus 1 here, and this it will be 0, this it will be 1 and 0 here. After that I think it will be as it is, 0 0 0 1. So this is the matrix. Let's see this was the D or not. Yeah, this is the D. So this is an interesting fact that we can do. I mean, if we are multiplying an invertible matrix to a matrix, that means we are doing some elementary row operation. And if we are doing some elementary row operation, that means we are multiplying by an invertible matrix. So here is the application, that if we are doing, and how to obtain that invertible matrix, that is also clear here. We will do matrix corresponding to each elementary row operation, and we will obtain that matrix. So this is the, so this will be the answer. Okay, and that is also the answer it is given. Second question is that consider the matrix A in question 1. That matrix we have written. The matrix B such that A and B are row equivalent is the matrix. One of the matrix is given here, and other matrix is given here. So here what we will do, we have to do elementary row operation. So before doing elementary row operation, we have said that how to do elementary row operation. First, suppose we have the same matrix, we will write same matrix: 1 4 0 1, 2 1 0 1 4 0 1 0 2 1 0 minus 1 0 1 8 0 2 0 0 1 2 0 1. This is the elementary matrix. This is the, sorry, this is the matrix actually, not elementary. This is the matrix A given. Now it is saying that after elementary row operation, what will happen? We are not going what will happen, because we can stop some places and answer will be that one. So we just do elementary row operation of that matrix, and how to do that elementary row operation. After that, we will go to the row reduced echelon form and do some problem. Okay, so what elementary row operation we are doing here actually? So let's first, what is the process to do the first elementary row operation and to get the row reduced echelon matrix and all those things. So let's follow the process. First process is that we will replace 3 4 operation, we will do at simultaneously. First we will replace R2 dash, that means R2 will be replaced by R2 minus 2R1. Okay, and R3 will be replaced by R3 minus R1. What is the target to do here is that first take the first non-zero entry of first row. Okay, let's take the first non-zero entry of the first row here. Okay, and if it is 1, then it is okay. If it is non-1, then then you can do one thing, is that you can multiply that row by a suitable scalar to make it 1. For example, suppose instead of 1 we have the matrix. Suppose this is the matrix: 1 0 2 1 0 minus 1 0 and all these things, 0 1, and suppose we have all these things. First non-zero entry of the first row is 4. That is not 1. So what we can do? We can do is that we can multiply this row by 1 by 4. Okay, so then what will happen? This row will be 1, 1, 0, 1 by 4. So we'll get the first entry 1. So first target is that first finding the non-zero entry of the first row. If it is in first place, then we'll and it is 1, then we will not do anything. If it is not 1, we will do the scalar multiplication. For example, we have a matrix A. For example, we have a matrix A. This is the matrix. For example, our matrix is given this way. I'm writing the last row firstly, and it is like as it is. Okay, 1 8 0 2 0 and whatever. I think I missed. Yeah, 2 1. I just interchanged some of them. But my point is that if the first elementary is non-zero entry is 1, but sorry, first entry of the first row is 0, but the below entry is non-zero, then interchange with any of the row to get the non-zero entry at the first place. Is it clear? I hope it is clear. If there is any doubt, I mean, this is something little confusing, but if it is there is any doubt, you can ask. My point is that first take the first row, and if the first entry is 0, then look at whether the below entry of that 0 is on that column basically is 0 or not. If it is 0, then okay. If it is not 0, then interchanged with the with a non-zero, I mean row here we have the non-zero entry. Suppose we have 0 0 1 0 0 0 0 1 0 0. So what we'll do, here is the first entry of the first row is 0, but all the entry below is are not 0. The only non-zero it has place 1. So what we have to do, we have to interchange row 1 and row 3. This is what my point. And after that, if that entry is not 1, for example that is 4, then after interchanging we have to multiply 1 by 4 to make it 1. So all these things are already here. First non entry of the first row is um, first entry of the first row is actually non-zero, and that is already 1. So we'll do this. If it is not 1, what to do? I have already said. If there is any doubt or need to repeat, then you can just tell me and I'll repeat. So, and then what is the main target? Doing all these things, the main target is that suppose we got 1 here after interchange or if it is needed or multiplication, then target is to make all the element here 0, but we can do only row operation. Okay, one warning is that sometimes during the row operation some person mistakenly do the column operation, just add or multiply or interchange two column. That is not correct, that is not possible actually in this setup. Okay, why that not possible? If you have two equation, a1 1 x a2 y is equals to suppose some b1, and a2 1 x plus a2 2 y is equals to suppose b2. If you can't, what I want is that we can't interchange this and this we can't interchange, right? Then variable will be something disturbed. Okay, but we don't want to disturb with variable will be as it is. We just want to add or subtract the row. This is what we are doing. So that's why during elementary operation, don't do any by mistakenly even a column operation. Okay, because column operation is not needed here, even not correct here, first of all. Okay. So now elementary operation first target is to make the non-zero entry 1, and after that making all other entry in below 0. So for that we will do the necessary row operation. So that is the only choice is that we need to subtract the row 2 by multiplying row 1 with 2, and we can directly subtract the row 3 row 1 from row 3. So that is what we are doing, and these two operation actually we have done here, right? R2 minus 2 R1 and R3 dash is equals to R3 minus R1, right? And so after doing this elementary operation, what we get actually, we get, okay, that this is not written, so we need then multiply again. So let's do it by hand. So first row is not changing, right? Okay, so let it be as it is. Second row, we just need to multiply this 2, that will be 2 8 0 2 0, and subtracting it. So this will be 0 1 minus 4 minus 7 0 minus 1 minus 2, that will be minus 3 and 0. Writing correctly. Yeah. Minus 3 and third row will be 0, 1 minus 1. I mean, we'll just directly subtract the row 4 and write. So this is the matrix. So directly subtract, I will subtract this row 3 from row 1 from row 3, that will be 1 minus 1 0, and 8 minus 4 is 4, and next will be 0 minus 0, 2 minus 1 is 1 and 0, and after that it will be as it is, right? As it is. Now what we can do is that, so all the entry is make already I mean done 0. Now what we'll do, let's find the second row. Let's come to the second row. First non-zero entry of the second row is minus 7. What we can do here is that, this is the formality I'm just saying. What we need to do here is that we have to multiply minus, subdivide minus by minus 7 to make it 1. So let's do it. Um, or we can do one more thing here, is that we can interchange this with this, but that is also doing same thing. Okay, let's do that. So one, uh, just a minute. 14010 is there. I'll just multiply minus 7, that will be 1 1 0, 3 by 7 0 0 4 0 1 0 0 1 2 0 1. This is the thing, this is the matrix. This will obtain from here actually. Okay, now what is happened here is that actually R2 is replaced by 1 by minus 7 R2, right? This is what happened. So So this is what happened. So in that case, now my target is to do what is that, similarly making all other entry of the, this is the point, okay, making all other entry of this column 0. That means we have to make this one is 0, this one 0, this one 0, this one 0. Let's do the operations. We will do the required operation. What is the required operation? First is that we will replace R1, I mean row 1 by row 1 minus row 2. Note that this one will not change after doing this operation. So this will be then 1, uh, sorry, multiplying by 4 row 2, 4, multiplying after multiplication 4. 4 row 2. This is what we are doing. So after multiply, okay, if we multiply just to for rough, 0 4 0 4 3 12 by 7, this is the fourth row will be, this is the second row will be, and if we subtract it from row 1, what it will happen, 1 4 minus 4 is 0 0 1 minus 12 divided by 7, that will be minus 5 by 7, and 0. Yeah, this will be 0, and second is this one will be as it is, this is as it is. Now what we'll do, I just want to make this element is 0. That's why what we need to do is that we need to do that r3 dash is equals to r3 minus 4r2. Okay, 4r2 is this. So r3, if we subtract it from r3, that will be 0 0 here. Second entry is 0, and 1 minus 12 by 7, that is again minus 5 by 7 0. 1 minus 12 by 7, yeah, minus 5 by 7. And now what we'll do, we'll make 1 0 here, 1 0. So how to do it is just to subtract it, r4 r4 dash is equals to r4 minus r1. Okay, we'll sorry, r2 how that 0 1 minus 1 0, 2 minus 0 is 0, and 0 1. This is the thing, right? This is the matrix we are getting. Okay, though I think answer we got, what is answer required here, that after elementary operation what will be B here. I think we, oh, that is in first level, I think. This is the first level. This was the answer actually. No, no, not this one. This one is not matching all of them. This is the answer, first matrix actually. That 1 minus 3 1. one. Yeah, first matrix. But okay, I am just doing the elementary row operation. How to do elementary row operation? Let's see. Let's do that. That is what we are doing actually. Now what we will do here. So now let's go to the third row. Third row. Third row. First non-zero entry here. But here is a entry below of which there is a two. Right? That is non-zero entry. So that's why we need to interchange. So interchange row 3 and row 4 will be interchanged. Okay, that is 1 0 0 minus 5 by 7 0 0 1 0 3 by 7 0, and we are interchanging 0 0 2 0 1 0 0 0 minus 5 by 7 0. This is the matrix. Now what we not need to do first is that we want to make it 1 here. Okay, let's do it. 1 0 0 minus 5 by 7 0 0 1 0 3 by 7 0 0 0 1 here 0. It will be half. Then we are just multiplying. We are just replacing r3 dash is equals to 1 by 2 r3. This is what we are doing. 0 0 0 minus 5 by 7 0. And the last non-zero entry in the fourth row, the non-zero entry is this. So I want to make it 1 here. So we can clear that what operation we just need to do, that is just multiply suitable thing. That okay, that doesn't matter actually. Okay, I'll do one. First thing is that, okay, let's do the first thing here, that R1 plus R5, that will be replaced by R1 will be replaced by this. Then 1 0 0 0 here, sorry, minus R1 minus R5. Then it will be, because minus 5 by 7 here, minus 5 by 7 here. So 0, and after that 0, or we can directly, don't do that. Sorry, don't do that. You can do without doing that. What we'll do here is that just to multiply R5, replace R5 by R5 into 7, multiplication by 7 by 5. So 0 0 minus 5 by 7 here, 0 here, 0 1 0 3 by 7 here, 0 here, 0 0 1 0 half here, and 0 0 0, it will be 1 0. This is the thing. Now what we'll do here, we'll just need suitable multiplication so that it will be 0. How to do that? Just to multiply row 1, row 1 plus row 4. 5 by 7 row 4. If we multiply it and add it, it will be, and row, this will be row 1 dash is equals to, and row 2 dash is equals to row 2 minus 3 by 7 row 1. Then what will happen? This will be 1 0 0 0 0 0 1 0 0 0 0 0 1 0 half here, 0 0 0 1 0. So this is the matrix. So this matrix is called row reduced as well as echelon matrix. So what is the row reduction process? The process whatever I have said. The process says that we will have to do the elementary row operation. And how to do the elementary row operation to get the row reduced? So let's first do the let's first understand the what is row reduced matrix here. Okay, what is the definition of row reduced matrix here? That's what I just want to um, point out. So row reduced definition, just let an m by n matrix A is said to be row reduced if first non-zero entry, the entry in each non-zero non-zero row of A is equal to 1. Okay, this is the first condition. Second condition is that each column of A which contains the leading, this is called leading one or leading non-zero entry, contains the leading non-zero entry of some row has all its and it is 0. So what is point is that first saying that the first non-zero entry of each row should be 1. Second is that, and if a column contains the first non-zero entry of some row, then all other entry of that column should be 0. Okay. So here is that matrix. This is the row reduced matrix. You can look at the first non-zero entry of each row is 1. We can look whatever the first non-zero entry of each row. And if a row contains the first non-zero entry of some row, if a column contains the first non-zero entry of some row, then that all other entry of that column should be 0. So what is what is leaving here is that suppose we have a matrix this 1 0 0 2. Okay, this is the thing, for example, and 0 1 0 3 0. So this is this, if you just matrix, this is the matrix, that this is row reduced matrix. Why this is row reduced matrix? First non-zero entry of each row is 1, there is no doubt. And second thing is that if a element contains the first non-zero entry of some row, so then all other entries should be 0. So note that here 2 and 3, they are not first non-zero entry of any row. So that's why in that case, we don't need that they should be 0. All other entry on that column, just if we write 1 here, suppose this is 1. So then if though here is 1, to become it is a row reduced matrix, what is needed here is that here is needed, or we can write one more column can be written, that is one more row can be written, that is 0 0 1 0 0. Suppose we have this thing, or suppose we have this thing, 1 here 1 here. Suppose this is the matrix, also a row reduced matrix. Why this is row reduced matrix? I just want to, I am writing this type of example to clear that what is row reduced means. First non-zero entry of first row is 1, all other entry is 0, there is no problem. First non-zero entry of second row is 1, all other entry is 0, because you can clear that first non-zero entry of the second row can't be here, because all other entry of one column in the column of this first column need to be 0, because 1 is the first non-zero entry of the first row. The second thing says that each column of A which contains the leading non-zero entry of some row has all its other entry 0. So that means if 1 is the first non-zero entry of first row, so then all other entry on that column, if it is that should be 0. That is first thing. Second thing is that, so that's why, that is the reason first non-zero entry of the second row can't be here. Okay, it is at least it can be here. It can be here also. For example, we can write it as this way: 0 0 0 0 1 0. First non-zero entry of the second row is here, right? First non-zero entry need not be at the 2 2 position. Okay, that is not necessary. Okay, first non-zero entry of the second row is here. Okay, just 1 minute. So this row can be completely 0. This column can be completely 0. There is no harm. Okay, this is row reduced. This is still row reduced. And the first non-zero entry of the second row is 1. Obviously, the first non-zero entry of the second row can be here or can be here, can be here or all other position. But I'm just trying to say this is the first non-zero entry of the second row, and all other entries are on that column. On that column is 0. Similarly, third non-zero entry is at this place, and all other entries are 0. Now, if we add a row here, still this is row reduced, right? Because first row is completely 0. There is no non-zero entry. What is the problem with me? Right? There is no non-zero entry. First row is 0. Also, this is no problem with this. If we write this, still this is a row reduced form. Why this is? It is satisfying these two conditions properly. Okay. First non-zero entry of the first row is here. Right? Right? First non-zero entry of the first row is here. And all other entry, so second condition satisfying all other entry below is 0. Okay. First non-zero entry of the second row is 1 here. All other element on that column is 0. First non-zero entry of the third row is here. All other entry on that column is 0. First non-zero entry of the fourth row is here, and all other element on that column is 1. So this is row reduced form. Even we can write one more thing. We can add 0 row above also. We can add 0 row above. Okay. Just a minute. I know how to do it. Yeah. So what I'm saying that let's do change it to and one more row. 0 0 0 0 0 0 0 0. So this matrix is row reduced. This is row reduced I am saying. But next what I will say that row reduced echelon matrix. Okay. So that is just needs some more things so to get the row reduced echelon form. Row reduced echelon, a matrix A, M by matrix, and M by N matrix A is said to be row reduced if first one A is row reduced echelon. If A is row reduced, it should be row reduced. First condition it is. But this is not all. It should satisfy more condition, more other two conditions. The condition that every row of A which has all its entry 0, which has all its entry 0, all its entry 0 occurs below every non-zero row. Every row which has non-zero entry. Every row which has a non-zero entry. That means all the 0 rows should be below. If a row has all entry 0, so that row should be below. And all the row which has all non-zero entry, at least a non-zero entry, they will be at least on those row. I mean, on the 0 row, above 0 row. Third thing is interesting, that is also maintaining here. This, I mean, how to understand this thing. If row 1, 2 are the non-zero row, suppose if a matrix can have fixed number of non-zero row, right? It does not saying that all other I mean, suppose a matrix has m number of row, so in that case it can have, for some k less than equals to m, it can have k number of non-zero row. Okay, so 1 2 are the non-zero rows of A, and if leading non-zero entry So obviously one first one is that we have r number of non-zero row. So that means total row is m. R number of row is non-zero. That means m minus r the number of row is zero. So that means we have first r number of row. Okay, and after that we have this row are non-zero, this row are non-zero, this row are non-zero, and after that we have row which are zero row, right? So first row, the first non-zero entry will be at some 1 comma some k position, 1 comma some j position, something like that. Okay, first non-zero entry, that is 1 because matrix is row reduced, so first non-zero entry should be 1. Okay, so so I think this is clear. So I mean whatever I'm just going to say, that will be on the basis of this. Leading non-zero entry of row I, that row I occurs in the column ki. That means for I equals to 1 to 1. That means first non-zero entry, that means first non-zero entry 1, because this is row reduced, so first non-zero entry should be 1, is at entry 1 of the row, or of the row I, okay, is at I ki position, I comma ki position. So I mean three things is that first A should be row reduced. Second thing is that every non-zero row will be above of the zero row. This is clear. These two are very clear. Now the third one is the third fact. Suppose we have matrix where according to the first and two condition, I mean suppose matrix was row reduced. We to maintain the second condition we do the row interchange operation. So after that we have all zero row are here and all non-zero row are here. Okay, all non-zero row are here. Okay, so so for each row have a non-zero entry. They are first one to all this way will go up to one. First each row has a non-zero entry. So let's first row has the non-zero entry at the position ki. First row need not have non-zero entry at the position. First row need not have entry non-zero entry at the position 1. Okay, so we can have like this. I'm just writing all other entry. Second row, this is the K1 position. That is what K1 means. Second row has non-zero entry. It does not affect that. The second row can have non-zero. Okay, there is one more thing also I have not written. Sorry for that. Then yeah, that interchange also be like this one. K1 less than K2 less than all the way KR. What is that? Second row can have non-zero entry like here. 1, second row can have non-zero into 1 0 0 all that, and for example let's all other entry are below are 0, for example, for now. Okay, for now all other entry in below of this row is 0. Is there any problem in listening or in video? I mean maybe it is not visible. If there is any, you just write in message even if you're not able to speak, because okay. So now my point is that I don't know why this is working. Okay, sorry. Okay, my point is suppose all other entry are 0. This is the 0 row. So this is row reduced. This is row reduced. There is no problem with that. Okay, but this is not row reduced echelon matrix because thank you. Thank you for confirming. Because why it is not row reduced echelon? It is satisfying first condition. It is row reduced. Second condition, every zero row are in below of the non-zero row, but it is not satisfying the third condition. What third condition say? Suppose first two row has non-zero entry, okay, and the column, this is the K1 and this is K2. The position where we have the non-zero leading one. That is what we are asking. First non-zero entry one of the row I. So for in case of one, this is at K1, this is K2, but it is not satisfying this condition, k1 less than k2 less than kr, I mean all the way go less than kr. So this is not happening. So to get this, what we have to do, we have to do the interchange these two rows. So after interchanging, we will have 1 0 0 all this way, 0 1 0, and this is 0. Suppose we have here 2 3, we have that does not affect. I mean, this is not matrix, but suppose we have 2 3, and after that we have 0 1 something like that, and this is the sub, for example, matrix. This is the matrix. Initially it was like 3 here, 0 here, 2 here, 3 here, 0, no, not 0, this is 1 here, 0 here, and these are the initial matrix. This is row reduced. This left hand side, this is right hand side matrix is row reduced. Okay, this right hand side matrix is row reduced, but this is not row reduced echelon matrix. To get row reduced echelon matrix, we have to you have to interchange row in such a way that the position where the first non-zero entry of each non-zero row has, in that case it will have this type of order. Okay, to get this type of order, we will interchange this. This is the row reduced echelon matrix. So this is the row reduced echelon matrix. So what is the process? First, to do the row reduction of a matrix. Whatever we will have, we will have. Don't worry. Second step is that we just interchange. We just take all the zero rows and it will convert. It will, I mean, send it to send it to below of the non-zero rows. Okay, and that by interchanging row operation. Third, third what we will do, and all the non-zero row are in above, so we have to do some interchange in such a way that k1 k2 kr will be placed that way. For example, okay, if we go to this particular matrix, this is row reduced, no problem, but this is not row reduced echelon. What is the first problem? First problem is that zero row, there is a zero row in above. So to solve this problem, we have to do the interchange of row. So suppose we have done interchange of row and we get zero row here. Zero row here. Okay. But still it is not solving the problem. What is the problem here? First non-zero entry is this place. Second non-zero entry is this place. If this is K1 and this is K2, obviously K1 is equals to 5 or 6. K1 is 6 and K2 is equals to 1. So obviously K1 is not less than K2. So what we have to do is that, and there is an obvious choice is there, here it was one. Obvious choice is that we have to send this row here. I mean, something, what we have to do here is that we have to first take, this will be first row, I'm just pointing out, this will be first row, this will be second row, this will be third row, and this will be fourth row, and this is fifth row. If we write that way, we will get the row reduced matrix. Okay, so I will write short here just to understand. So this is not, usually this matrix is not, so I will, okay, suppose 0 was there, I will just interchange, as we have not place to write here, I mean I will just write us in short form. But this matrix is not, this is not row reduced echelon form, not in row reduced echelon form. Okay, to get row reduced echelon form, I'll just saying to interchange what will be the exact position, and we have to do the according changes to get that position. Okay, so I'm writing is to get it in the row reduced echelon form. This will be, okay, still there is a place sort. To get it in the row reduced echelon form, this will be the, here is total fifth row, this will be the first row, this is first row, this will be second row, though the second column is 0 completely, that does not affect. Okay, this will be the third row, this will be fourth row, this will be fifth row. So now suppose we have done the row reduction of this matrix. So this matrix, if you look at this matrix is completely in row reduced echelon form. Okay, This matrix is completely in row reduced echelon form. So what is the advantage of row reduced echelon form have? That is that, for example, I will not write that in the explain, just I will write here. Suppose this is the matrix. I will write this matrix in below and to suppose uh, let a row reduced echelon matrix is this. Let Ax is equals to B. A is a 4 by 4 matrix. I am writing A1, A12, A14, A21, A22. Okay, I will write instead of 4 by 4, 4 by 5 I will write. That's better because we always need to have n by m will be better. I mean to understand at least. 2, 5, A31, A32, A35, A41, A42, A45. Okay, this is the matrix. Okay, so and B is equals to I'm writing B1 all the way B4. This is the thing. B will be 4 by 4 matrix. So let after row reduced echelon form, after row reduced, and when we uh, do this row reduction process, we will do similar. For example, suppose we have Ax is equals to B, and after row reduction, what we getting A dash x is equals to some B dash. Let A dash be the row reduced row reduced form, which is in row reduced echelon form of A. This is unique. For a matrix, the row reduced echelon form is unique because we can't do anything else after that. I mean, we can do, but that if we try to maintain the row reduced echelon form rules, that three rules, it would be row reduced and the zero rows will be below, and that ordering of the non-zero entries that is increasing, then we can't do anything else after that. So that's why row reduced echelon form is always fixed. So, for example, this is the process, row reduction process. Okay, let's let it be the row reduced echelon form of A. Row reduction process simultaneously simultaneously done on right hand side, on right hand side also. That means what I want to say here, is that I am just interchanging two row. Then we will also interchange the corresponding BI, BJ. That is what simultaneously. We are multiplying each a row and adding with some other row. Also, we are doing the similar thing here. So that means we are doing the same operation. We are doing the same operation on the matrix A mod B. This is not mod, this is just to symbolize. This is nothing. Okay. This will be then we initially A was 4 by 5 matrix, right? So this is will be 4 by 6 matrix. Now it is clear. 4 by 6 matrix. So so 4 by 6 matrix, as it is 4 by 6 matrix, after row reduction, suppose we have A dash. We have similar operation is done here, B dash. Okay. This is the thing then. This is the then particular thing. I mean, whatever row operation we are doing, will do it simultaneously. I mean, initially it was A1, A, A4, 5. Now we will add 1. A21, A25, add 2. This will all go, it will go 4, 1, A4, 5, B4 is there. We are already doing operation here. Whatever we operation do, and after that we get the matrix A dash. For example, we are assuming that this B1 is there, but we are not doing anything. But whatever we will do here, we will do here. I mean, whatever interchange we will do here on this row, that will simultaneously also occur here. Okay. So in that case, now this system, this matrix, okay, this matrix as a special name is there is that is called augmented matrix. Okay, this is augmented matrix, and Now next thing is that okay, interesting fact here is that here we will be know whether a system has solution or not. If there is a solution, then what is the number of solution, either finite or it will be either unique solution or infinite number of solution. That is that is can be given some different way. That is by rank or number of non-zero row. Or that is like this is that if the system will have solution if number of non-zero rows of A dashed is same as number of non-zero rows of A dashed mod B dashed. What it is mean? Suppose after row reduction we get that matrix. I'll write that matrix is initially 1 0 0 0 1. I'll just look at once. What was that matrix? Okay, 0 0 only at place only at fourth row it is. Sorry, only at third row it is half at the last. Okay, so this is the 0. So if we take that matrix of the initial matrix, then we will get this matrix, right? 0 0 0 0 0. Sorry, this is 1 0. This is half and 0 0 0 0 1. Oh, sorry, this is 1 here. 1 0. This is the matrix A dash. This is A dash. So we have done some operation on B. Suppose A is clear. What A is? A is that this matrix actually. A is this matrix. We have done some row operation and get after row reduced echelon form we get this matrix actually. So this is the A and we don't know what is B, but I'm just for example assuming that the system was like AX equals to B system is given and we have started AB and after elementary row operation we get here and this will be like B1 dashed, B2 dashed, B3 dashed and B4 dashed. For example, now I'm just saying for example matrix was initially like one more row is there and something like we get this type of things, but b5 then what is the number of non-zero row here? Suppose a is this, a dash mod b here is this. What is the number of non-zero row here? First row, second row, third row, fourth row is 0, but fifth row of a dash, if we just consider a dash is only this portion. A dash mod b is this full part. Okay, so then what is the non-zero row here? Non-zero row of a dash is actually 4. But what is the non-zero row of A dash mod B dash? That will be 4 if B5 is equals to 0 and 5 if B5 is not equals to 0. For example, if this is not 0, the number of non-zero row into this full matrix is 5, right? But if that is 0, then this is 4. If this is 0, then number of non-zero row into A dash mod B dash is 4. So system will have solution if the number of non-zero rows of A dash is equal to number of non-zero rows of A dash mod B dash. Why it is happening? Because having this type of thing, for example, we have B5 for which B5 not equals to 0 is something saying that we give a equation like 2x plus 3y is equals to 5. Another equation is 4x plus 6y is equals to 11. This system will not have solution. Why? I'm just giving quick this is the thing 4 6 11. This is here you will have that. Suppose this is the thing, so how will get? I'll just do that. Suppose 2 3 5 is there. I'll just subtract from this row 2 by multiplying by row 1. That will be 4, that will be 0 0 1, and after multiplication it will be 1 and whatever is done. Okay, that is done. For example, we have the row reduced form will be 3 by 2 5 by 2. This is the row reduced form. So here this is the A dash, this matrix is A dash. Okay, but this is the full matrix A dash not B dash. This is why this non-zero entry is coming here, because this system can't have solution. Why this is? Because this, if you multiply this equation, what will happen? 4x plus 6y is equals to 10. So there is the problem. It is 11 showing. So obviously there will not be, because that is something not absurd. This is something absurd, right? if a system has solution for some fixed x and y, it is satisfying. So 4x plus 6y should be 11, but it is getting 10. So first equation is contradicting. I mean, solution of the first equation does not satisfy the solution of the second equation. I mean, what are the x and y satisfy this equation? Those x and y will not satisfy this equation. Or whatever, what are the xy satisfying this equation will not satisfy this equation. But solution is that common x and y which satisfy all the equations, right? So that's why here is no x, no solution. So this is what happened when there is no solution. That situation is called inconsistent. If a system does not have solution, okay, and if a system has solution, then it is called consistent. And if a system has solution, then it is called inconsistent. So this is what the system of linear equation and row reduced echelon from all these things are there. Now I'll just quickly, I'll take 7 to 8 minutes in total from now. So now we'll just quickly what is the vector space and yeah, what is the vector space here? Okay, vector space definition I will not go, but vector subspace. And to prove I will prove a vector subspace whether it is subspace or not. That I will prove in one equation. A subset V W of a vector space V. You know what is vector space, that I am not talking about. Vector space V is said to be subspace is said to be V over a field over F over a field F, said to be subspace over F if W itself is a vector space, right, over F. That is what over F. And that is equivalent to saying is that for any alpha beta belongs to W and C belongs to the field F, C alpha plus beta should be contained in W. So if this is happening, then we say, so that means if this is happening, that for any alpha beta belongs to W, this is called addition operator. So better to write is in C dot alpha vector beta. This is the additive operation. This is scalar multiplication operation. Multiplication operation. Multiplicative operation. That means multiplication by scalar. By scalar or elements of same thing. Elements of the field are called scalar. That is what scalar means. Scalar multiplication. But note that one point I just want to share here, want to say is that when we say a vector space or something, so there is, I think you have know there is two things. One is addition, called addition. One is called multiplication. These addition and multiplication are not the usual addition and multiplication. For example, I'm just saying 2 plus 3 equals to 5. This addition is addition. We know that. I mean, this is a class of addition. This is a class of multiplication. And 2.3 is equals to 6. This is multiplication. That's true. But these two can be different also. For example, this is a very interesting question will be, let's take set, I'll take set R plus that is equals to actually what are the positive real line, R is x is 0, not 0 is not included. Then define addition from R plus cross R plus. Don't be like I mean scared this thing scores cross. This is just want to say that if we have element alpha and beta in R positive, that means positive real number. Let's define alpha plus beta is equals to alpha dot beta. This is usual real number addition multiplication. and scalar multiplication, that is from the field f is real here. Okay, for example, over R, this is the field, that is equals to field. Then this will be from R cross R plus to R plus. Vector space should be like that way. So what is here? Suppose we have C comma C comma, here is alpha. This is going C dot alpha, right? This is the operation. I am defining this alpha to the power C. So note that here addition is not addition, here addition is multiplication. And here scalar multiplication, what I am saying, that is something exponential. This will form a vector space. That is what interesting. This is a vector space over R with the operation mentioned above. So that means if we see a question and giving addition, so don't do addition always. What is addition means there? If it is not written anything, no, that means usual addition. If it is written something that addition is this way, this will form a vector space. Why this is a subset of real number, right? Though operation are different, this will form a vector space. Just to check, I'll give the two operation only, scalar, and the distribution property is something always creates problem. So first check that real number with this addition operation is an abelian group, and that is clear because a alpha plus beta, that is equals to alpha dot beta, and we know this is the usual. This operation is usual multiplication. This is usual real multiplication in real number. Okay, alpha plus beta equals to, this is the beta dot alpha, that is equals to beta plus alpha. Okay, so this is vector space. All these things will be. I will just check only one thing, that suppose C dot alpha plus beta. This is the distributive property. Something creates problem. Usually all other properties satisfy. Sometimes distributive property creates problem, and sometimes this type of property. And this is already here. If you take beta equals to 0, and what is 0 here? That I am just trying to say a little bit. That is equals to, it will be alpha plus beta means C dot alpha beta. Here is dot, is this dot. C dot alpha dot beta. This is usual multiplication. This is the dot scalar multiplication. Alpha dot beta to the power C. That is what means. That is means alpha to the power C dot beta to the power C. That means C dot alpha. That means this C dot is that scalar. This is equals to C dot alpha dot C dot beta. There is two dot. One is usual multiplication, one is circled. There is, so please try to understand these two. This is very interesting thing. Oh, sorry. And this multiplication says that alpha plus C dot beta. Okay. Just a minute. Sorry. Yeah. So that's why this is making a vector space. And vector subspace means this. What is that? Vector subspace means, yeah, this is I mean, I just want to make, so usually written as C alpha plus beta should be in W whenever alpha and beta belongs to W and C belongs to scalar F. Okay, so when you want to check is set is subspace or not, first one thing you need to check is that whether 0 is there or not. Zero element of the main vector space, mother vector space, from where it is becoming subspace. So in that case, that 0 is there only. If 0 is not there, so that can't be subspace, because whenever we take C is equals to 0 and beta equals to 0, this element will be 0, right? 0 dot alpha is 0 plus beta is 0, so that's why it will be 0. So 0 should be there. If 0 is not there, so no need to check anything. Okay. So one where is that? One example was there. So I'll just easy short example. For example, this example I'm just trying to say. Let V be the real vector space of all functions, and after that we'll stop. from R to R, which of the following sets is a subspace of V for all f such that fx square equals to, and for all f0, this will be why. Suppose we have two functions f1, f2, and scalar is real number. Here real number, right? Yes, real number f1, f2. So what we want to show is that cf1 plus f2, this function satisfy this condition. So let's take 0 is equals to this will be c of f1 at 0 plus f2 at 0, because this is usual function property we know, that is c of f1 at 1 plus f2 at 1, because f1 and f2 are coming from w. This is the set, right? This is the set. Let's take all such functions. This is the set w. So that means it is satisfying this condition. So that means f0 is equals to f1, and this to satisfy for both the cases. f1 0 plus f2 0. So f1 and f2 satisfy this condition. f1 0 equals to f1 1, f2 0 equals to f2 1. So that means c f1 plus f2 whole at 1. So that's why this is becoming vector space. But this is not vector. This is not subspace. Why this is not subspace? Because if you take function f of x square, I just want to say, let's take two function f and g for which f of x square is equals to fx whole square and g of x square is equals to gx whole square. So whether f plus g that at x square, that is not equals to f plus g at x whole square. That will be only when a plus b whole square is equal to a square plus b square, but that is not usual, right? So that's why it is not the case. Similarly, this will not be case. Why this will not be case? Because suppose we have two function f and g for which f of minus 1 equals to 3 and g of minus 1 equals to 3. Then f minus g, what will be at the point minus 1? That will be 3 minus 3. That will be 0. But f minus, so that implies that f minus g is not in the subspace of W. Similarly, this will not be because 3 is there. We can do the same. Forget about this thing. We can do the same thing so that 3 will, this will not be. So this will not be, this will not be, and this will not be. So this is the case. Okay. I'll stop here. If there is any problem, please ask. So, or we will meet in the next Saturday. And till now, if you have any doubt, you can ask me. Okay, in my mail ID that I'm writing here, you can ask any question doubt in my mail ID. I'll not saying that I will answer you exactly on time, but I will try to as much as fast as possible. Please. Okay. So you can write this in this mail. So otherwise, if you don't have any doubt, please, if you have any doubt, please ask me. And otherwise, we'll meet on next Saturday. And there will be a weekly feedback, I think, form will be given. Please fill that feedback form of this regarding on that basis of class of this. You can fill whatever you are getting from this class, you will fill accordingly. Okay, so is there any doubt? Please type here, sir, your mail ID. Yeah, that will be better. But when I will upload the notes, so that's why ma21b018 just a bit of smail.iitm.ac.in. Yeah, this is the mail ID. If you have anything, if you have any questions, you can write to me in that mail ID. Okay, I will try to answer as fast as possible, but I will obviously address those problems in the next immediate um, tutorial. So yeah, so please fill that feedback form. Maybe if it is circulated, I don't know whether it will be circulated or not. If it is circulated, please fill that feedback form. Whatever your preference, whatever you get from this tutorial. Okay, so if there is no any doubt, I will. If there is any doubt, please say it, or I will stop in 1 minute then.